Hello there, and welcome to this second film about gases. It's the fourth in the series of 6 about the kinetic theory. This one deals with the relationships between certain not properties but conditions that gases might be under, namely pressure, temperature, volume, and the number of moles. And we give those things symbols: pressure, volume, number of moles, and temperature. And we're going to have a quick look at why those ideal gas assumptions that we made in the last film, what they've got to do with actually these laws being simple laws that we can pretend are obeyed. Okay, so oops, I don't want the pen, I want that. Okay, so here we are. Here is the first relationship we're going to look at. We're looking at the relationship between pressure and volume. Okay, and we're looking here at what happens to the pressure. So this is what happens to the pressure, this is our dependent variable, as we change the volume of the container. Okay, so this might be a pump or a syringe or something else that you can change the volume of. Okay, and we notice that as the volume gets very large, the pressure gets quite small. Okay, it drops because those particles that are in the container can't hit the walls of the box as often, and so they don't exert as much pressure. As the volume gets smaller and those particles are crammed into a smaller space, well, they hit the walls more often and they exert more pressure. Just a quick look here at one of our ideal gas assumptions, the one that they take up no space. Well, what this gas seems to imply is, what this graph seems to imply, is that if I had a very, very, very high pressure, I'd eventually get to zero volume. Okay, so that's one of our assumptions, that the particles take up no space. But I mean, clearly that makes no sense. That's like saying if I pressurize something enough, it's eventually going to disappear from existence, right? Okay, this graph may strike you as looking like an inverse relationship where the pressure is proportional to 1 over volume. Okay, so if I double the volume, the pressure will halve. Okay, this is another way of showing that same relationship because we've plotted pressure against 1 over volume and we've got a straight line. So this shows that there's a linear relationship between pressure and 1 over volume, or in other words, they're proportional to one another. Okay, that's actually called Boyles Law, but we don't need to worry about what the law is called. Okay, just what it tells us and why it should be the case, okay, in terms of particles. Moving on and looking at pressure and temperature, okay, we are observing what happens to the pressure of a gas if we change the temperature in this graph. Okay, so we're heating a gas up and we're noticing that its pressure is gradually increasing. Why should that be? Well, we're making the particles move faster because we're increasing their temperature and therefore their kinetic energy. Okay, so they hit the walls harder and more often and exert more pressure. Okay, what we'll notice here is that eventually you'll get down to a temperature where no pressure is exerted at all, and that means that the particles have stopped moving, and we know that they can't unless they're in a perfectly insulated container, which you can't have in this universe. So we've got this temperature scale. This is actually measured in Kelvin, not degrees centigrade. Okay, and this shows that at 0 Kelvin, which is called absolute zero, and this is just the theoretical temperature. Okay, that's absolute zero, and when we get to there, that's when all the particles have stopped moving, and that's when the pressure will be zero. There won't be a pressure. Okay, this graph shows, I suppose, it looks a bit more basic really, that there's actually this kind of odd region down here where you will get pressures even at very, very low temperatures. So I mean, it's another way of saying it is to say that you can't get down to absolute zero. Okay, so if I drop the pressure, I'm never going to get to this very, very low temperature. Okay, moving on. This is something called Avogadro's law, and it relates the volume and the number of moles of gas. Okay, as I've said before, you don't need to know the names of these laws. Okay, I might just go back to that previous graph there and just write down what the relationship is. Okay, the pressure is proportional to the temperature, so if I double the temperature, the pressure doubles. But notice this will only work when the temperature is in Kelvin. Okay, because if I double the temperature from 10 Kelvin to 20 Kelvin, I've given the molecules twice as much energy. if I go from 10 degrees to 20 degrees centigrade, I haven't doubled the temperature. I've actually gone from 283 Kelvin to 293 Kelvin. All right? So whenever we're measuring temperatures here, we've got to go for Kelvin. I suppose if we had the graph of temperature and pressure, and we had temperature in degrees centigrade here, then we'd actually still have quite a high pressure at 0 degrees centigrade, okay, and then it would come until we eventually got to minus 273.15 degrees centigrade, okay, that's 0 Kelvin, very chilly indeed. Okay, so back to this one, Avogadro's law. All right, Avogadro's law relates the volume of a gas to the number of moles of it, and I suppose Avogadro was quite lucky here. He got a law named after him for basically saying if I double the number of gas particles, the gas is going to take up twice as much space, which maybe seems quite intuitive to us these days. But what this means is that the volume is proportional to the number of moles. That's why we get this straight line. If I double the number of moles, say from 0.4 to 0.8, I'll double the volume. Should double the pressure as well if the volume didn't change, because there's suddenly twice as many particles hitting the wall. So the pressure is also proportional to the number of moles, so long as I keep the volume the same. Okay, the volume will only be proportional to the number of moles if I keep the pressure the same. All right, it's not fair if I allow the pressure to go up, because that basically means I'm putting more gas in, but I'm not letting the container get bigger. That means that's what pressurizing a gas in a certain container is, really. Okay, so here is that relationship again. As the number of moles increases, the volume increases, and it's a straight line relationship, so the volume is proportional to the number of moles, so long as we keep the pressure constant. Okay, all these things put together lead us to something called the combined gas law. Okay, if I rearrange this to find P, I can see that P equals nRT V, and that's another way of saying that pressure is proportional to 1 over volume, so long as I keep the temperature the same. What were some of the other relationships I looked at? We looked at the number of, the pressure and the volume compared to the temperature. Well, the volume equals nRT P, so this equals T times over P, which means that volume is proportional to temperature. Okay, and so would pressure be, because I could just say that pressure equals nRT on V. Okay, so pressure and volume are proportional to temperature, so long as the pressure is kept the same in the case of the volume, and so long as the volume is kept the same in terms of pressure. One thing we haven't yet looked at with these things is this thing here, that's called the gas constant. Okay, gas constant is 8.314. It's written on your data sheet. There's no need to remember that quantity, but without that number put into this relationship, it doesn't make any sense. You'll need to use this formula, PV equals nRT, in some of your mole calculations. But right now, I suppose all we're saying really is that this combined gas law is a combination of those other gas laws we've seen in this film, and it relates all the quantities together in one nice, neat formula. Okay, and that's the end of that one. The last film in this series, although it's the 5th one, is out of 6, is about vapor pressures. The 6th one is a few practice questions. Okay, so this next film about vapor pressures is the last one that contains new theory. Can you just check before you move on to it that you've understood the theory in this one and that you've made a note of all the important key points?